Hello. So, in a previous sort of video work, we introduced the idea of L'Hopital's rule, and sort of one of the common problems when we introduce L'Hopital's rule is that it is such a powerful tool and it's so useful that students tend to sort of use it on everything, like, swatting a fly with a jackhammer gets a little overkill at times. So in this video, we're going to be talking about sort of times where you want to step back and take a look and maybe not use L'Hopital's rule, even though technically you could, and to see why that might occur. Okay, so by way of sort of introduction, there's this old adage, right, that when you have a hammer, everything looks like a nail. This idea that when you sort of have a tool that seems to work really well, then you start wanting to use it on everything. So psychologists call this functional fixedness. It's this tendency to get sort of stuck in a rigid way of doing things. So in this particular sort of setting, it would be the equivalent of like every time you see, a limit that you get 0 over 0 or infinity over infinity, you sort of immediately use L'Hopital's rule without really thinking about what you're doing or why you might want to be doing that or not. So we aim in this video to give some clues as to sort of when you might want to use it, but sort of more importantly, when you might not want to use L'Hopital's rule. Instead, sort of look at some other methods, okay? So as we sort of were saying, when you encounter this sort of format, right, this 0 over 0 limit or infinity over infinity limit, it's very tempting to just sort of immediately apply L'Hopital's rule because it's sort of already in that form for you. But it can save you considerable time, effort, and frustration if you sort of take a second and look at why this thing is in that form, like looking at the format and see if there might be some obvious sort of simplification or algebraic step that you could do to sort of bypass that problem in the first place and thus not have to sort of go through L'Hopital's rule. Now you might be asking like, yeah, but I could still do it and still get an answer, right? So why bother? So let's look at some examples. So here we have sort of a classic L'Hopital setup, right? So we have a polynomial over a polynomial and the limit's going to 0. So if I actually compute this limit, right, if I just sort of plug in that 0 and see what I get 0 over 0. So it's true, we could apply L'Hopital's rule, but if we did that, we would get another polynomial where we would have x's on every term on the top and the bottom. Plug in 0 again, we'd get another 0 over 0 limit. Now, that's not saying it didn't work, right? We'd have another 0 over 0 limit, so we could apply L'Hopital's rule again. But we would get another 0 over 0 limit. In fact, we'd have to apply L'Hopital's rule a bunch of times before we get something other than 0 over 0. And so I'd have to be taking, 6, 8, 10 derivatives, depending on how far you're going, before you'd actually get to the point where you would get an answer. Or looking at the actual formula here, right? Looking at what I have for polynomials, I can notice that everything in the top has an x, everything in the bottom has an x. That's why plugging in 0 is getting me that 0 over 0. And in fact, everything has at least this x cubed. So if I divided the top and bottom by x cubed, right, if I canceled that x cubed factor from everything, then the top would go to 0, but the bottom would end up going to 1. And I could just compute the limit straight up. The limit would be 0. I didn't have to do any derivatives. I didn't have to do anything, really. I didn't have to make, I didn't have to use L'Hopital's rule. All I had to do was cancel an x cubed factor. So that would be much quicker and much easier than applying L'Hopital's rule, 3 or 4 times over again. So this is one example where, yes, you can use L'Hopital's rule and it does get you an answer. It just takes a lot more time and effort to get there. But you don't always get an answer from L'Hopital's rule with some of these setups. Again, if you sort of just blindly run in. So here's another example where if I plug in this 1 coming from the right on my equation here, I'm going to get something of the form infinity over infinity, which again, that's in L'Hopital's form. So I could go ahead and take L'Hopital's rule. If I do that, right, just immediately go to L'Hopital's rule and apply it, well, then I'm going to end up with a thing that looks like 1 over x minus 1 on the top, right, taking that derivative. And the bottom I'll end up with 1 over x minus 1 plus 1, right, because I'm going to have this minus 1 is going to go away, but that plus x is going to turn into a plus 1. And if I try to plug in 1 again, I'm still going to get some sort of infinity over infinity. So again, like here's another example where like, okay, I did L'Hopital's rule because it was in the right form. I get another thing where I could apply L'Hopital's rule again. So if you sort of just do that, right, if we just keep taking derivatives, it's going to keep being infinity over infinity, and you will never get to a stopping point, right? So let's just look at a couple levels of this derivative and see what happens. So if we take another derivative, right, a second derivative, I'm going to end up with this 1 over x minus 1 on the top still, right? And if I plug in 1 up here, I'm going to get something infinitely large. Same down here, I'm going to get something infinitely large. So it's still infinity over infinity, and I could go to the next one, which is, again, going to get me something that is infinity over infinity. And I could go again and get something infinity over infinity. But the problem here is that every time I'm doing the derivative of the top and bottom separately, all I'm doing is increasing, right, that denominator's in each one, the denominator's power, right? So this is going to a 4, and that one's going to a 4. But if at any point I sort of step back and look at what I have as an overall function, right, even like here, this is just a thing over itself, right? I'm dividing something by itself. So this is really just 1. So if I just canceled that out and gave, right, and had equals 1, I would be all set, right? So if you sort of just blindly process that it's still in the right form and keep going forward, this is a very easy trap to get sort of pulled into and waste lots of time instead of sort of stepping back at any given step and saying, okay, what is my overall thing? Can I do some sort of simplification? Can I do any sort of algebraic technique that sort of cuts down whatever is causing this problem, right? In the first example, it was a common power of x that I could sort of take out, and that's what was causing the 0. Here it's having that x minus 1 on the denominator, but if I actually simplified this, my x minus 1 on the denominators for both of them would go away, and I would get just 1, and then I would be all set, right? So stepping back and sort of taking a look, if you've done L'Hopital's rule more than once, it's almost always a good idea to sort of step back and take a look and see if there's some way that you can sort of simplify something to get out of doing this a whole lot of times, okay? All right, so what do we do? So it can be easy to lose track of the bigger picture when you're applying L'Hopital's rule, right? It's really easy to zero in and be like, it's of the right form. I'll just keep applying it over and over again. And this is sort of very tempting because it's a very quick and easy thing that works on most of the problems that are in that form. So it sort of usually works, and thus it's sort of tempting to just assume it will always work. But if you blindly just apply L'Hopital's rule whenever you see the opportunity, it can actually result in a lot more work in the long term, as opposed to sort of going and stepping back and seeing if there's some way that you can simplify the problem or, do some sort of algebraic technique to at least cut down on the number of times that you need to use L'Hopital's rule. Okay? So that is that.